talk about what is a black body. Define an ideal black body, please. So spectrum, I'm assuming it's cleared. Yes.
Yes, sir. Yeah. So
What is a black body?
black body is an ideal body which absorbs and emits all frequencies of light.
That's not correct. Define again. What is an ideal black body?
It's a perfect absorber and emitter.
See, an ideal black body does not need to absorb everything which is thrown at it, but it should not retain anything which is absorbed by it. That's the idea. That is, if I'm going to be having an ideal black body, it should not retain
Hmm. Sir, your voice is.
everything which it has absorbed.
Sir, can you repeat? Your voice was not audible.
An ideal black body is something which will emit everything which it has absorbed. That's the idea here.
Okay.
Any form of energy which it is absorbing, it doesn't matter what form, it will emit it out. It will not keep anything for itself. That is
So
basically what is going to be an ideal black body. Okay, now hmm, ask. You seem to have something to ask.
no, 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 nothing.
Okay, what was your issue regarding ideal black body there?
No, sir, I was just like okay, nothing, sir. I
Ask.
got it
You
clear now.
feel weird about things. Ask. See, the problem is this: you feel shy about stupid things. You see all of that you do in your school because there are other people to basically feel shy around. तेरा
Hmm.
इज्जत की बात होगा यहाँ पे. What nonsense do you have? You don't have much izzat, and that's how it should be. You can learn only when you do not have a fear of being wrong and a fear of being called out for being wrong. Talk, ask. What was your doubt there? What felt weird?
Sir, like initially, I thought that it was a perfect absorber. So I thought if you put if you use that for absorption spectrum to like you create an absorption spectrum out of it, it would be completely black because it absorbs all the source of light, something like that.
Technically, a really perfect black body is going to be something. If you really have to go about even more exactly, yes, we can argue that it must absorb everything. That is very much acceptable to an extent. It's not a bad conjuncture, though it does not have to do that. But still, let's assume it does for the sake of the argument right now. Where will it go then? What was your thought there?
If it does absorb everything, that means the but then not considering it does not emit anything, then the spectrum should just become black, right?
Why did you assume it will not emit anything?
Yeah, I don't. Okay, my bad. That's why I was like
Hmm. The reason why your question came up is because you had a problem with the black body
definition.
definition,
Yes, sir, yeah.
mainly because you went with your perception of black and what you have learnt about black color, and you assumed that has to somehow fit in here. You're not wrong, but you forget that you still see black, right?
Yeah, yes, sir.
You're, I'm guessing that is where your question comes from to
Yes,
some
sir, yeah.
extent.
Yes.
It is not a wrong thought process. That is a way to what to say, look at things. But there are a couple of more problems here. The black color which you see is only absorbing all the visible part of the spectrum which is going to be black.
Hmm.
So if I look at it from a different spectrum part, it is not going to be black. What is true black? Something which absorbs as you put it across everything and anything, but it is also emitting everything and anything. That also has to be there, because if it is not emitting everything and anything, how will I be seeing black? What does it mean if I see the color black? There is still light bouncing off of it, correct? That's why I'm able to see that object, right?
Yes, sir, yeah.
So if it is not bouncing, I would not be able to see it. The fact that I'm able
Correct.
to see it means it is bouncing light,
Emitting.
emitting.
Sir,
Uh,
does this have anything to do with black holes? Like,
Again, what is a black hole?
not, I mean,
No, you have some idea. That's why you brought this up. So
yeah,
let's diverse that. No problem. What is a black hole? It absorbs everything,
absorbs everything, yes.
but does
But
it
we
emit
don't,
anything?
no, I mean, no, I don't know actually. Not too,
It does emit something called as Hawking radiation over like
yeah, yeah,
enormous
Hawking.
amounts of time, but still, you're going to be having, technically speaking, it emits nothing. From our layman perspective, it emits nothing. So, is that a perfect black body?
No,
No. Now, what is the black body which you are learning about over here? Let's say I'm taking a dosa tawa or a
mm,
chapati tawa. If I heat that shit, what happens after enough amount of heat is given? It starts emitting light,
yes, yeah,
right? It gets red hot, yeah, white hot, whatever,
yeah,
right? So now think what is happening there. You are giving energy to an object, enough energy, and by just providing energy in the form of heat, it is starting to emit light, right?
mm,
That is what is happening.
yes, sir.
That is a black body. That is a type of radiation which Max Planck actually studied. When he says he studied black body radiation, what does it mean? It means he studied, what to say. So when we are going to be having, we are talking about black holes or what we were talking about? Tawa. So when you're going to be having a dosa tawa or some other tawa, that is the kind of black body which Max Planck actually studied. He gave them energy in the form of heat, and then he saw that they were converting it into light and giving it out. He studied those radiations which were emitted by that black object. That is basically
Mm,
why it's black body radiation. Okay, next up. Do you have any more questions along these here, on these lines here?
no, sir. Nothing else.
Are you sure?
Yes, sir. Yeah.
Confirm?
Yes, sir. Yeah.
Okay. Now, what did Max Planck do? What is his work? You just said you understood whatever you need to understand there, no? Explain.
With respect to this black,
With respect to what he did. Black body radiations, he studied them.
yeah,
What did he do after that, after he studied them? What did Max Planck do?
showed that
Yes, please.
energy is quantized. Mm,
Originally, what he decided was that, what to say, energy is going to be quantized is fine, but how would he have concluded that?
yeah, mm,
He basically ended up
so,
comparing. We talked about how people measured stuff, right? So what he did was he compared the energy of a particular wavelength of light with, what to say, another, a different wavelength. He noticed that energy is inversely proportional to wavelength and directly proportional to frequency. So if that is the way it is, then there is some factor which we are not seeing yet, which basically is able to break down a beam of light into its individual components, which we call now as photons. So what he did was he ended up quantizing energy. What does quantizing energy mean? It
it
means
can
that
be
having
broken.
the light emitted by these black bodies, he decided that that light had to be emitted by individual photons, which are basically, how to explain? I'm too sleepy right now. Lunchtime ke baad is always not a good time.
Mm,
Give me a second, I'll go wash my face and come.
yes, sir.
Basically, he studied the photons route, and not photon. He studied the light emitted by the black body radiation. He concluded that energy is proportional to frequency or wavelength, which basically means that intensity is not going to be related to the energy aspect here, not
Understood.
with respect to frequency and wavelength. That means I'm going to be having the individual, or the light which is basically shining has to travel in the form of tiny tiny packets. It is not going to be a continuous form of energy. So if it is in the form of packets, that is basically what is quantization, right? What does quantization mean? Quantization means any
Broken down.
what to say, entity or any form of energy which you're having, you can always break it down into what to say, individual pieces. That is effectively what Max Planck's work was. What does it mean if something is quantized?
Can be broken into.
Okay. Instead of asking you questions, let me just directly give you the pointers which you need to understand here. If I'm going to be having, let's say, money taken, okay, money is quantized, yes or no?
Yeah.
Yes.
Yes.
Why? Because anything which we are basically doing, we can basically transact, any transaction which we do is going to be by a fixed quantized amount of money,
Yeah.
some whole number multiple of some random thing. Hyderabad, for instance, now even for $1, 1 rupee, we cannot do anything. So Hyderabad, the lowest denomination which you can use is probably 2 rupees or even 5 rupees.
Yeah.
So definitely 50 paisa is all gone. Okay. So if that is the case there, think what is the consequence of that. If, let us say I am interested in buying chocolate. Can I go and ask them for a lick? No.
No.
Right? Not
No,
going
sir.
to be feasible. I can go ask them for some amount of chocolate which corresponds to some money which is quantized.
Yeah.
That is feasible. But I can't go ask for an unquantized amount of chocolate.
Yeah.
So the idea here is when money gets quantized, anything and everything which is associated with money is also quantized. Right?
Correct.
So anything and everything which is associated with money is also going to be straight away quantized.
Yeah.
So if I'm going to be having energy being quantized,
Everything is quantized.
everything which is associated with energy is also quantized. So
Yes.
now let's go for what is meant by a quantized orbit. So when we talk about an orbit being quantized, what does that really mean? What that means is when you consider Bohr's model, Rutherford's model wala problems absolutely simply do not apply there at all. Why? Because Maxwell's theory is applicable for waves. It is not applicable for quantized objects. Why? Because the moment you quantize something, it is not a wave. You are breaking it down into a piece.
Wave is continuous.
Correct. So
Yeah.
that means it is already a discontinuous object or a discontinuous entity. That means the moment Bohr started applying Planck's quantization, all of Maxwell's shit gets kicked out. That is one way of looking at it.
Hmm.
Now let's talk about what exactly quantized orbits mean. So when I'm going to be looking at energy being quantized, energy is quantized.
Yeah.
Max Planck has proven that properly beyond a shadow of a
Yes.
doubt. So now
Yeah.
what happens over here is when you're going to be having energy being quantized, anything associated with energy is going to be quantized.
Hmm.
In this case here, we are going to be having angular momentum of the electron in a given orbit has to be
Okay.
quantized.
Yes, sir.
So if it is quantized, what that means is the electron, when it is revolving around the nucleus, it simply cannot have random values for angular momentum.
Hmm. So,
It can only have specific designed and assigned values. It cannot have random values. It
yeah.
simply cannot. So what Bohr did was He experimentally calculated
That.
the angular momentum associated with electrons in orbits. This he calculated experimentally and he confirmed that it has to be something which is quantized around the value h by 2 pi. For instance, in India, we can say that money is quantized around the value 1 rupee, right?
Yes. Yes,
The
sir.
lowest denomination we can technically use across the country is 1 rupee.
Yeah.
Same way, he sat and did this experimentally and he
Mm.
got this quantization value as h by 2 pi. Obviously, if h by 2 pi is the smallest denomination, what did he do? He decided, okay, this is the smallest denomination. So let me now define my new orbits where the electron has to be as spaces where the angular momentum of the electron has to be only a whole number multiple of this, because quantization means it has to be existing in this packet, right?
Yes, sir.
So what is the smallest packet possible of this? 1 into h by 2 pi.
Yes, sir.
Next smallest packet is 2 into h by 2 pi. As I
Yeah.
said, I cannot buy chocolates in licks. I can buy them in pieces, but I can only buy them in pieces.
Yeah.
No one's going to sell it to me in a lick. Even though technically I can say that one lick of a Cadbury chocolate is going to be maybe 12 paisa worth, but that's not going to be meaningful here.
Yeah.
You understand the idea here? That is
Yes, sir.
basically what a quantized orbit means. So when you're going to be having the orbits of the electron according to Bohr, he said that the angular momentum has to be whole number multiples of h by 2 pi. This is what it means. Why is the angular momentum quantized? That is because energy
Energy
of
is
the
quantum.
electron has to be quantized as well. Bohr could not calculate that energy value experimentally,
Mm.
or rather, he could not calculate the quantization value for the energy experimentally, but he could calculate the angular momentum's quantization value. You
Mm.
understand the idea here?
Yes,
So
sir.
that means if I'm going to be having the electron present in an atom in say n equal to 1, n equal to 2, n equal to 3, n equal to 4, whatever it is, the electron simply cannot and is not allowed, mathematically speaking, to exist between n equal to 3 and 4. Why? Because if it is between n equal to 3 and 4, its angular
Angular
momentum
momentum.
should be something between 3 into h by 2 pi and between 4 into h by 2 pi.
Yeah.
That is not an allowed entity because it's
Yes.
not possible. So, quantized, fixed, stationary. Not that it cannot move from one level to another, it can do so, but it will have to basically disappear from its level and then reappear in the next level. And how can it do it? By either emitting a photon or by accepting a photon.
Mm.
So if a photon of light comes and gets absorbed by a particular electron, then the electron will disappear from its current level and go to some higher level, reappear back in some higher level.
Yes, sir. Yeah.
And if the same photon is falling down from a higher level down to a lower level, what will
Energy is
happen?
emitted.
Exactly.
Mm.
So it will disappear from the higher level, reappear in the lower level, and throw out a photon of light. You understand what's happening here?
Sir, why are you saying it's disappearing and reappearing like that? Like,
Because the space in between is basically not allowed.
yeah, like it's not jumping literally.
Yes. Now the problem here is this. When I say disappear and reappear, it feels weird mainly because we are talking particles. But the reality is electron is not a particle.
Yeah.
It is
Mm.
a wave. We will
Mm.
talk about what that means if you have any doubts on that part. For the time being, the particle nature theory is you have to think of it as disappearing and reappearing.
Mm.
Next question. What do you
Sir,
have
I
again?
have, yeah,
Ask. You should have
like
more now.
along, like, when do we consider an electron to be a wave and when do we consider it to be a particle? Can we just do it whenever you want? Like,
No. The electron is a wave always.
okay.
Okay. Any object which is going to be of a time scale much lower than ours
Mm.
will almost always have extremely tiny mass. The smaller and smaller the mass of the object is going to be, the more and more pronounced its wave nature becomes. For the electron, talking about it as a particle is not correct. We have to talk about it as a wave.
Hmm.
Why is it that Bohr's model still works, even though he considers it completely as a particle? In Bohr's model, the electron is completely treated as a particle by Bohr. That is why he is able to calculate the electron's velocity, radius,
Yes.
energy, all that shit.
Hmm.
Why does it still work? Well,
Let's break. Yeah. De Broglie also.
this particular constant h by 2 pi, which he had calculated experimentally, is something which pops out directly from de Broglie's equation,
Yeah. Yes.
which basically means that Bohr, yes, he did not assume that the electron is a wave, but he calculated a variable experimentally, which basically was like a constant which associates the wave nature for it directly.
He thought he was correct for this, but then, yeah.
No, he
Hmm.
was correct.
But
He was
then,
very correct. But the reality is, he had done the work through experimental details and through real
that's
hard
the.
work, through
Hmm.
sheer hard work. He did not understand what he was calculating.
Yeah. Yes.
Later on, theory basically directly suggested that, oh, what you have calculated is the
Correct.
variable or the constant which accounts for all of the wave nature. How do you convert an indefinite integral into a definite integral? Add a constant.
Constant. Exactly.
That is basically what has happened over here. The wavy electron is converted into a particle nature by introducing a constant h by 2 pi. So does that mean the electron is not a wave anymore? No. The electron is absolutely a wave. But Bohr's model is one of those rare models where he has approximated the wave nature perfectly nearly, which is why he won his Nobel Prize as well. Next up, what else do you have to ask?
Okay. That's it for now. So, yeah.
That's it for now. I am way too sleepy right now.
Yeah.
Till when are you available exactly?
So like before 5 anytime.
Before 5 anytime?
Yes. Yeah.
I'll take a 20-minute nap and I'll get back to you.
Okay, sir. Sure.
We'll close class for now.
Okay, sir. Yeah.
Bye bye.
Bye, sir.